Yeah, happy to have you, Tanja. Please share your screen and give us your talk. I see myself out. I'm over there.
So, yeah, so I'm trying to share the screen. I hope everybody can see it. Yeah, great. Yeah, then thank you very much, Arne, for the kind introduction, and thanks for inviting me to Mainz, even if it's though only virtual, and I'm happy to come physically, maybe next year, whenever it's allowed, but it's great to see you all again. And yeah, I will take the next 45 minutes or so to report a little bit on ongoing work that we've been doing at PTB, the German National Metrology Lab, and I'm also associated with Leibniz University, Hanover. So the title of the talk is Optical Clocks based on Ion Coulomb Crystals. I just would like to give you a short overview of what we're doing here in my group, in my research group. The name of my group is actually Quantum Clocks and Complex Systems, because we're trying to combine both sides. So tackling, opening up many-body quantum systems, complex systems, for precision spectroscopy and to improve time and frequency standards. So in total, we have now 4 project groups, Arbeitsgruppen. One is dedicated, the focus of the research is many-body physics with trapped ions. So this is where we're doing topological defects and energy transport and such things. Then we have a group dedicated to the multi-ion clock operation, where we use mixed indium and ytterbium species Coulomb crystals. Then we have a technological group that is building compact and scalable linear ion traps and already next generations of it. And last but not least, we're also setting up now a user facility ion traps for the Quantum Technology Competence Center at PTB. So in this talk, I will give you a short overview of the 4 things. I will go a little bit deeper, of course, into the multi-ion clock business, into precision spectroscopy. The second part of my talk will be to give you a little bit an update what's been going on in the many body dynamics in Coulomb crystals. This is of course closely related because both fields of research profit from each other. If we're having a good control and understanding of the many body dynamics of Coulomb crystals, we can scale up our ion clocks one day even further to 2D and 3D systems. And a short outlook of my talk will be then dedicated to future ion trapping platforms, so the technology side that we're working on. Yeah, so let's start with the clocks. I'm sure you all have seen such a graph many times, the impressive improvement of optical frequency standards going further and further. In some labs now starting to cross the border of 10⁻⁸. And yet there seems to be no really fundamental limit at sight. At the moment, it's all technological problems we're dealing with. So why is 10⁻⁸ at all interesting for us? And yeah, what are big goals of our research? I mean, one of the main motivations I like to use for introducing such a clock talk is using novel quantum clocks for geodesy, for relativistic geodesy. Because this is really when the 10⁻⁸ becomes really important. This is when we're talking about 10⁻⁸ clocks, this is where geodesists open their ears to us, start listening and become really excited. Because since our laboratory clocks at the moment can resolve such frequency differences, what we can do with modern clocks is that we actually can resolve the height in the gravitational field of our planet. And 10⁻⁸ just means exactly that we can resolve the height difference of 1 centimeter. So if I measure time here, or I elevate my clock by only 1 centimeter, then I already can see the time difference, the gravitational redshift that Einstein predicts and that we observe on a daily basis when we do international clock comparison. And for geodesists, this 1 centimeter height resolution is really the interesting thing. And I will show you in a moment where there are possible applications. So this is exactly where clocks are now meeting classical and quantum gravimeters that have so far been used to map out gravitational fields. So what we're interested in when we're talking about relativistic geodesy is basically about mapping out the geoid. This is how our planet looks like if the surface would be covered by water. Of course, it's a slightly exaggerated, as you can imagine. So the bumps that you see here would be on the order of 100 meter. So this different maxima and minima in the gravitational field of our planet are maximum 100 meter height. And this shape was actually first introduced by Carl Friedrich Gauss, who was a son of Braunschweig. And he called it at that time the Erdfigur. So the geoid is basically the equipotential surface of the gravitational field of our Earth under gravity and rotation. So as I said before, if everything would be covered by water, the surface, this is the shape that you would see because water naturally follows the equipotential surface lines. And why it's important for us is actually because, first of all, it describes the water flow. To understand the global water household and also how masses are changing on our planet, think of global warming, it's becoming increasingly important. But already if we look from gravity satellite data, which have nowadays a resolution of the order of 100 kilometers, and then we compare it with gravity measurements that have been conducted on ground with classical gravimeters, we observe big deviations. And just across Europe, from the north of Scotland to the south of Italy, you see differences from plus half a meter to minus half a meter roughly. So there's a big discrepancy between earthbound measurements and satellite data. And a lot has to do with different tide gauges that are used, you know, the mean level surface. The northern countries refer to the Northern Sea, southern countries refer to the Mediterranean Sea. And the mean surface of the ocean is actually not a good measure because it depends on the salinity of the water. It depends on ocean currents. It's also a very complex system. So with clocks, actually, we believe that in the future, now that we achieved the 10 to minus 18, we can contribute to this Earth observation, and clocks will serve in the future as height references. That's something that was already proposed in the late 70s and 1980s, but now we're getting there. And if you're interested in more details, I just show you a quick example from a recent review that we published. A very local example. So if you think of our highest mountain in Germany, the Zugspitze, roughly 3,000 meter high, again, due to global warming, the permafrost is melting and it's diminishing. So geodesists expect actually that our Zugspitze is shrinking by something like 1 to 2 centimeters per year. So every year it's getting shorter. But the problem is with GPS, we cannot resolve such a small height distance, especially on the mountains with a turbulent atmosphere. So if you would put a gravimeter there to see how the height or the masses are changing, you wouldn't be able to resolve this because you have local mass variations due to the annual snow cover, which is changing over the year, or some groundwater changes. So if you look at the numbers, the signal due to the height loss is something like 3 times 10 to minus 9 G per year. That's what we expect. But the signal due to the snow cover change is 50 times 10 to minus 9 G per year. So the local gravimetry could not differentiate this. And this is exactly where clocks come in, because we're measuring the equipotential lines, so the difference in potential. And that scales, of course, with a long range with 1 over r. So here we are not sensitive to local mass variations. So this is just one example where clocks can be really helpful for geodesists. And if you're interested in more details, I would refer here on our, 2 years ago, we published this review article on that. So let's start a bit with the technical side, optical clocks. How do they work? What's the state of the art in our labs? For those who haven't seen it yet, I will just quickly show the slide. So the heart of an optical clock is, of course, the local oscillator. That's a laser in the optical domain. And the laser itself is first stabilized to an ultra-stable cavity. In our lab, we have something like 1 times 10 to minus 16. And this ultra-stable cavity serves as a short-term reference. So this can give us extremely good frequency stability for a few seconds of time scales, up to maybe 100 seconds. But then, of course, this frequency reference will drift away due to temperature changes, local air pressure changes. So it's not a good clock for long term. That's where the atoms come in. So a stable, pre-stabilized laser is already excellent then to do precision spectroscopy onto the atom. And with the laser then, we can resolve basically the quantum jumps in an atom. We love to use here highly forbidden narrow transitions. That's why the stable laser is very useful. And then we try to lock the laser onto the atom. So we're measuring the quantum jumps and seeing if our laser resonance is near resonant to the atomic resonance. So this gives us then the long-term stability. And as an atomic reference, you can use different things. You can either use neutral atoms that you store in an optical lattice so that you get a longer interaction time, or you use nowadays single ions that are trapped in an ion trap. The atoms, since we have many of them, they're at the moment the frequency standards with highest stability worldwide, while the single ions actually still hold a world record in accuracy. And I will tell you in the following a little bit about the ion clocks. Since this is what we're working on. As I think all of you know how ion trap works, I will not go into much detail. I just would like to highlight why are ions at the moment still holding the world record in accuracy. Well, as you surely know, the traps are quite extraordinary. So if you're talking about such RF Powell traps, they give us a very, very deep trapping confinement of several 10,000s of Kelvin. So for this reason, we can really have trap lifetimes of a single ytterbium ion, for instance, of many, many months. And we don't have to load very often. It's a really completely isolated quantum system in an extremely well-controlled environment. The ions are always trapped at E = 0, so that at first order gives us no systematic shifts. Thanks to this very strong and stiff trapping potential, we have a very strong localization of just a few nanometers. So that means we can map out every magnetic fields, electric stray fields, and everything with a very high precision, so that we really know what our atom, what environment it experiences. And in addition, if I'm dreaming now of a portable clock to go up on a mountain to do geodetic measurements, of course, the ion traps certainly can be engineered in a very compact and a robust way. And the present record actually is at the moment just reaching the 10⁻⁹ regime in terms of accuracy, and is at the moment held by the NIST group in Boulder. So this is the aluminum quantum logic clock. Now I was talking about accuracy, so how about the stability? This is another key figure that is important for atomic frequency standards, and this is basically about the statistical error.
Just a quick question, sorry.
Ah, yes, please.
So is there any squeezing involved in this high frequency precision?
No, actually, no, it's a single quantum absorber. It's really classical interrogation, no squeezing, no. To my knowledge, actually, there is no clock in this world that uses any interesting quantum techniques like entanglement or squeezing to really get a true metrological gain. Not yet. Okay. Not yet.
Is there any reason, right? Because in cavity 3D, in principle, you can do that, right? You can, for metrological gain, squeeze. You don't reach the same precision of clocks, that's true. There are other problems there.
Yeah, the problem is the noise sources. So on paper, you can write it down, and people have, well, observed certainly proof of principle measurements where they have profited from squeezing and such things, but only at the price that they had to actually deteriorate the local oscillator, and then they saw the improvement. But if you take the best local oscillators that are available in our laboratories, like I showed you this laser with 10⁻⁶, then you don't win from squeezing because you throw away signal and you get in other noise sources. So unfortunately, we're not yet at this point that our best clocks could profit from this.
I see. So essentially the question is, where's the best pen trap? And the Geoid turns out to have the best pen trap, and this is it, he gets a precise clock.
I mean, you really have to look very, very carefully what are the noise sources, and is it a white noise, and which time scales? Is it quantum projection noise that you're seeing? Do you have some aliasing, some Dick effect, some finite duty cycle? What is the noise of the local oscillator? And all this will tell you whether you really profit from any squeezing or entanglement. And at the moment, it's always better to push the classical bounds to get a better oscillator, and then we're winning like an order of magnitude than if you would do squeezing. But we're working on this, so in the future, at a certain point, it will come in.
Somebody will, definitely. Thank you.
Okay, so instability, the statistical error. So what's the state of the art there today? I show you here for a typical single ion clock, the statistics, and this is usually expressed in terms of the Allen deviation. So this is a modified standard deviation. How well you can resolve the frequency here again in relative units. In 1 second of averaging time, you start at around 10 to minus 15. And then if you want to resolve the frequency better, because I mean, systematics is nice. So if we claim we have 10 to minus 18 or 19, this is a systematic analysis and study on one side, but now I also have to measure it. I have to really find the mean value of the frequency out of this big noise I have. Yeah? So I have to be patient, I have to average, I have to wait and average down. And in roughly 1 day, the clock is then just crossing the barrier to 10 to minus 17. If I want to go further to 10 to minus 18 or even the 19 region that we're opening up, you have to average for many tens of days, yet even 100 days. And this is actually the fundamental limit of a single ion clock, because the number of quantum absorbers is 1, so this, the quantum projection noise is very high. And the quality factor Q, which is given by the frequency and the resolved line width, is difficult to push by yet orders of magnitudes. So this is where our multi-ion approach comes in, that some 8 years ago or so, we asked ourselves the question, why can't we just scale up such a single ion system to a many ion system? And by this, we would win linearly immediately in averaging time. This is by chance just a 37 ion Coulomb crystal. And that tells you if you do measurements on a single ion system, you get the same information in 37 days. Then here, if you do this in a 37 ion system, you get the same in 1 day. So you really win linearly with an ion number. And this is what we claim, that now it's really time for physicists in the lab to expand the experimental methods to manipulate and measure many-body quantum systems. And then when we have many-body quantum systems under a good control in a classical way, we even can think then of entangled clocks, squeeze clocks, entangled clocks that would even scale with 1 over n. But first, the basis is a really good control over such a quantum system on a classical basis. Also, quantum logic clocks could be scalable. And this is what we call quantum metrology. And we're using, of course, many tools as you here in the audience use when you're doing quantum information and simulation. I'm aware that also other people have already thought about the multi-ion approach. So in 2015, there was a nice paper by Mary Barrett et al. And Arnold et al. Coming up, and many follow-up papers that proposed lutetium ions, but they're targeting directly at a big Coulomb system of, they proposed 1,000 ions in a 3D Coulomb crystal. That was a theoretical study, and they are now on the way to experimentally realize it. Our approach is more a bottom-up approach. So maybe we're a bit chickens. So we are saying we want to keep the high level of control that we have over a small quantum system. So we're dreaming of something like 10 to 20 ions in such a linear Coulomb crystal to have this high precision of 10 to minus 18 or 19. And then we want to scale it up in linear areas of Coulomb crystals to make it really scalable. And like this, we can envision having 100 ions. The ion systems that we're using, these are ytterbium ions and indium ions. This is what we're dealing with. So indium is a very good candidate for multi-ion clocks, but actually also the ytterbium system is highly interesting on the octopole transition. That has also a really low quadrupole shift, and you can get a good clock there. This is actually how such a picture from our lab looks like. We have here an indium Coulomb crystal doped with ytterbium ions in the center for sympathetic cooling. And what I find very spectacular, this is really an image from the same CCD camera where we imaged both ions at the same time. So here we have indium ions that are fluorescing at 230 nanometer, and we have ytterbium ions that are fluorescing at 370 nanometer. And with some clever imaging system, we managed now to have a very sharp focused image of both ions at the same time. We just displaced the image a little bit, but the ytterbium ions would actually sit directly here in between the indium ions. Yeah, so what are the challenges now that we are tackling every day in our lab? I mean, why did nobody scale up a single ion clock to a many ion clock? Certainly many of them are of technology, a technical problem. So I'm thinking of the on-axis micromotion, distorted RF fields, the heating of ion motion that scales even stronger with many ions, the warming of the trap due to the large currents we have, magnetic field gradients, inhomogeneity, many technical things, everything to do with the ion trap, but also the control of the complex many-body system. And we believe we have found good solutions for all of these aspects to address. Well, this is how our design looks like. It's basically a chip-based ion trap where we can shuttle ions around. So we have a dedicated loading segment and then some protected spectroscopy segments. Like this, we can avoid the contamination in the high precision segments. It's a chip-based ion trap. Why are we doing this? Because we would like to have as monolithic structures as possible to get a high precision when we build it together, that we don't have to align many different things. So it's a rather monolithic approach. And we have either 2 or 4 chip ion traps. We have different generations of development there. Everything is done in-house by laser structuring. This is an example how such an ion trap looks like. So we do the laser cutting, the structuring of the LEDs, we do the bonding, everything ourselves. Everything has to be, of course, clearly non-magnetic, ultra-high vacuum proof at the level of 10 to minus 11 millibars, very precise. We're really targeting the micrometer level. Needs to have a very good laser access for the clock. We have onboard temperature sensors. That's a PT100 sensor with 30 millikelvin calibration accuracy. And this is how the process looks in a clean room. So we have even now upgraded to an industrial grade femtosecond laser. We are having titanium and gold sputtering machines, precision alignment tools. Recently, we also got a fine placer that has a precision of half a micrometer where you can place things together. We're doing flip chip bonding, thermocompression, ribbon bonding, wire bonding. So there we're definitely profiting from the great infrastructure that we have at the PTB campus. This is how it looked when in 2016 we put one of these first ceramic traps into our test vacuum chamber. It's still a very large testing chamber. You see here the protection against the ovens and everything, that there's no contamination. Then we do a hard bake out for something like 3 weeks to get the 10 to minus 11 millibar.
Yeah, sorry, but I have to say it looks like you wrapped the person.
We wrapped what?
You wrapped the person and you're baking the person.
Yes, yeah, we forgot the PhD student inside. You're right. Thanks for pointing it out. Yeah, so when everything was baked out and working nicely, we did then some characterization and measurements on this ion trap. First question for metrologists was, of course, what's the heating rate when we cool the ion to the ground state and then switch off the lasers, wait, how fast is it heating up? So we were very happy to see when we compared it now to the international ensemble of ion traps as published here in this review paper by Braunat, that our 3D chip trap, it's certainly rather macroscopic. That's why we're pretty much down here. But even within this large scattering range, we're fortunately pretty much on the lower side. So the heating rate is really less than a phonon per second at 600 kilohertz. Then also the the thermal environment we characterized successfully over the last years. There were many papers on this. And this year we also made it, last year, 2020, we made it on the cover of Review of Scientific Instrumentation, where we detailed and give a nice review report on this thermal management, where we can achieve a trap heating of less than 1 Kelvin, despite having almost 4 ampere of current flowing on the ion trap with thousands of volts. So this is all due to a good thermal management and characterization. We also measure time dilation shifts in this Coulomb crystals. So here you see basically this should be a 3D picture of ions in a Coulomb crystal, where we could resolve with atomic resolution the micromotion amplitudes. And this is the bar here. This is a scale of 1 nanometer. And this is basically what we observed. This is the motion of every ion spatially resolved in the crystal. And this is basically the micromotion amplitude, how it looks like. And with this, we could demonstrate for the first time that even in an enlarged ion crystal of over 300 micrometer of length, we could keep the time dilation shift to less than 10 to minus 19, which was definitely not obvious. And I will not go in all the details, but I just refer to our papers from 2019, where we published then the full error budget of such Ion Coulomb crystals in the ion trap. And we showed that we really can achieve then a systematic uncertainty in these traps at the level of 10 to minus 19, even for this extended Coulomb systems. Okay, now I talked a lot about the clock. I would also like to mention here briefly interesting things that we do with the terbium ions itself, not with indium, but with the terbium ions, because here the audience, I mean, you guys are more experts than me. So I would like to show you basically the status at PTB. And it's about the local Lorentz invariance, what I like to speak. Of course, we do also other measurements, local position and variance and so if you do clock. But let's focus on LLI. This is basically a repetition of the Michelson-Morley light interferometer. So that was first done in Potsdam, as you know, more than 100 years ago in this beautiful setup. And the question is there a preferred direction in the universe? Is the pillar of Einstein's equivalence principle really a solid pillar or not? And I know that people here in the audience have already engaged in very high precision measurements on the local Lorentz invariance. Here I would like to show you something of what we're doing. We're basically changing the light interferometer nowadays to atom interferometers, and then posing the question of preferred direction in the universe. The idea originally, I think, comes from the Hartmut Heffner group in Berkeley. He had a very nice paper in 2015 where he made the first measurement like this in calcium ions. So he prepared basically superposition states, or this was the proposal to go for the full entanglement then, to basically prepare different electron orbits. So prepare the wave function of the electron in a -1/2 state and in a -5/2 state. So we know that these electron orbitals look very different. So they have a very different preferred direction in space where you have the momentum of the electron. So basically these electron orbitals are very sensitive to different directions in space. If everything is isotropic, no problem, then the energy of such a system would be the same like the energy of this system. Or in other words, the energy difference between a -1/2 and a -5/2 state would be always constant in time. But if there's an anisotropy in space, so let's say a preferred direction in the universe, and then Earth is of course rotating in a sidereal day once around itself, so every 23 hours and 58 minutes, you're rotating around yourself. So basically our system would probe the different directions of the universe. And if there would be a violation of local Lorentz invariance, one would observe then a change in the energy difference between these states, 1/2 and 5/2, exactly at the period of a sidereal day. So that was this beautiful idea. And I did serious measurements on it. So the proposal was, okay, we have to look at magnetically sensitive states. Yeah, we're talking here of electron orbitals of -1/2, -5/2. So they're to first order Zeeman sensitive. So one solution is we either entangle them, as it's shown here, that was the Hefner proposal, or we do dynamic decoupling. That's actually a proposal coming from Roy Osiri's group. The recent state of the art that was achieved in Berkeley was in 2019. They published this, the full entangled system with calcium ions, and they could for the first time really go down to less than 5 × 10⁻19 in uncertainty. And when I'm citing this number, I mean here the local Lorentz violating Hamiltonian. So this amplitude C02, this is what they're probing, this is what they're sensitive. And for this, they could pin down now really to below 5 × 10⁻19. This was an extreme, huge improvement compared to previous light interferometer measurements. This was calcium ions. Then Zuber et al. Published,
very quickly, how they suggest to propose, how to suggest to protect entanglement and superposition over long times, which is the idea in this proposal.
Sorry, can you repeat your question again?
How do they suggest to protect entanglement for the very long time in which you have to measure this anisotropy?
Yes, sorry, I didn't explain it well. So look at this. This is basically the wave function if you have 2 ions. So ion number 1 would be in, I'll go back by 1 here. For instance, ion number 1 would be in -1/2 state. Ion number 2 would be in +1/2 state. And ion number 1 would be in a superposition between -1/2 and -5/2. And ion number 2 in the superposition +1/2 and +5/2. So if you take the global wave function, which is basically here the products between those, then you see that this state has a total spin of 0, and this also has a total spin of 0. So this entangled state of having here ion 1 there, ion 2 here, and the superposition, this is to first order Zeeman insensitive. And then basically what you have to do is to see if there's a phase evolution, if the energy of this system, which has is a -1/2 direction, if this energy would change now with respect to the 5/2 direction, while the Earth is rotating around itself.
Nice. Thank you. Nice to see.
And yeah, then there was this other proposal by Zuber et al. Coming up in 2016, where they calculated the sensitivities of other ions. I'm aware thorium is also a highly interesting candidate, and I think that's also being followed in Mainz, right? Which should have a very high sensitivity. But we at PTB, we have the terbium ion clock operational. So for us, it's the natural first step to go. And fortunately, terbium has also extremely high sensitivity to a possible violation of local Lorentz invariance. Because the F electrons are very relativistic, so they have large momenta. And Zuber et al. Calculated that in principle, we should get even up to 1,000 times improvement compared to the calcium results. Well, as you certainly know, the terbium single ion clock is world leading. So in Eckhard Pike's group, they have 3 × 10⁻18 resolution, and they're in a fortunate state to not only have 1 ion clock, but they have many. At the moment, they're actually operating 4 different ion clocks. So in a way, you can say it's also becoming a multi-ion clock, just that they have one experiment next to the other. And what they did is basically they compared 2 independent terbium ion clocks, then for many, many, many weeks, yeah, even months. And like this, they could they choose different quantization axis. So the quantization axis of one ion clock was like this, and the other quantization axis of the ion clock was there. And then again, they just waited about the sidereal rotation of the Earth, and then looked for this possible changes in frequency of one clock with respect to the other. And that was a very long measurement, as I said, to average for really many months. But like this, Sun et al. Were then able to really pin down again this local Lorentz violation coefficient to below 10⁻21. So this is at the moment actually world record. And together with Eckhard Pike, what we're about to do now is actually we're trying to improve that even further with ytterbium-172. Why? Because first of all, 172 has even a higher sensitivity than 171. And in addition, it's really scalable. So we really want to do now LLI test with many, many ions in one trap, where we have a lot of commonalities and common systematics, and which will allow us then to get a very high resolution in a much faster time, that we don't have to wait for half a year and comparing operational clocks, but that without clock operation, we can do a measurement in a single ion trap with many ions and get this result in a few days, and then like this average down even faster and push the limit further. And the way we're planning to do this is with a spin echo sequence, as it has been demonstrated by Shanif et al. With strontium ions. So this is basically, you have to bring the spin up to the F state, prepare some well-controlled magnetic sublevel here in the F state, and then you do such a spin echo sequence with microwave pulses where you rotate the global spin around in this F manifold. Like this, you can also then decouple it from magnetic field noise, and only if the energy difference between the magnetic sublevels is constant in time, then the complete full spin will always come back to the initial state. Otherwise, it will dephase and you will lose the signal. So this seems to be a really nice way to do. The big problem is just to excite and prepare the F state with a good quantum control is extremely difficult, because it's an octopole transition. The lifetime is 6 years, so it's ridiculously forbidden. The Rabi frequencies you get are really slow, and it's first order Zeeman sensitive. So you have very strong decoherence. And we were working on this for the last years, and we were very happy that it worked out. And in summer last year, in 2020, we were able to publish the first coherent excitation on this highly forbidden octopole transition in ytterbium-172, where we could see beautiful Rabi flops and a decoherence time close to 200 milliseconds. So this allows us really now for the first time to have really controlled quantum state preparation in this super forbidden octopole state, in the F state. And by doing this, we also we increased basically the accuracy of the known absolute frequencies of both octopole and quadrupole transition by more than 10 to the 5, so 5 orders of magnitude. Okay, so I have to watch a bit the time. It's time, I think, now to come to the second part of the talk, which will be shorter. So this is now about the quantum control of a many-body system, the Coulomb system itself. And so far I've talked and shown you results that have been done in linear strings of ions, so all at the nodal line without micromotion. But of course, we can also load larger amounts of ions. We can prepare 2D and 3D crystals, so even going to several tens or hundreds of ions. And every time when we're lower than 20 millikelvin or so, we get the formation of Coulomb crystals. The way we do this is basically the control parameter that allows us to determine whether I'm in the one-dimensional phase, two-dimensional, or three-dimensional phase is actually the aspect ratio of the trapping potential. So by tuning the confinement in radial with respect to the axial direction, we can choose what is really the equilibrium ground state. Is this a 1D, 2D, or 3D phase? So this is our experimental control. And the interesting thing in this ion systems is when we cross the phase transition, like here going from 1D to two-dimensional phases, you actually do some symmetry breaking phase transition, because you see here we have a rotational symmetry, here we have a mirror symmetry. And the global Coulomb potential, while it's here very symmetric, and basically the ground state is at phi equals 0, so everything is lined up along this line. When we're going to the two-dimensional phase, we are getting 2 local minima. And minimum 1 would correspond to this zigzag phase, and the other minimum would correspond to the zigzag, which is exactly inverted. So the system has to choose which of these two possible configurations does it take on. And that's really a second order phase transition, as Fishman and Giovanni Morici have shown. That makes it highly interesting because second order phase transitions, we know from Ginzburg-Landau theory, we can do beautiful things, and we can also look out for defects, topological defects that were proposed by theorists at that time. So what happens if we do this transient from linear to zigzag? We undergo this symmetry breaking phase transition in a fast way, faster than the ions can talk to each other, than they can communicate. Is it possible that we get some topological defects? And that was something that we studied in 2012 and 13 in parallel with the group of Ferdinand Schmidt-Kahler, who did such studies with calcium ions. And these are, I show you here the results from 2013, where for the first time we have seen the topological defects in our system. We have seen localized defects. You see where the ion was basically stuck between two domains. Here you have the zigzag, zigzag, and here you have the zag, zigzag, zig. So the two domains that don't fit to each other, and a local ion is stuck. Or here that's an extended defect where the ions are slowly reordering and they're really metastable directly on top of each other. We have studied then the probability of defect formation and undergone a test of the Kibble-Zurek theory and the Kibble-Zurek scaling. This we published back-to-back with Ferdinand's group in 2013, so ytterbium and calcium back-to-back publications. And we also followed up with Martin Plenio and the theorists. So this is a whole research area by itself. I will stay very superficial and just show you what you can do with these topological defects and use them basically as a platform for other nice many body physics. Because when we saw this picture, so we prepared a topological defect, and if you have a slight heating due to a glitch in the laser frequency, for instance, the topological defect leaves the Coulomb system, and you see that it really looks as if the atoms are sliding on top of each other, atom by atom, in really perfect way. So we ask ourselves, can we understand this? It's a complex system, it's self-organized, yeah, it's really like a molecule, like a protein. It has back action. Can we study friction and nanofriction here, similar to what people started doing with the biomolecules or with nano engines? Every time when you have perfect atomistic surfaces, can we study this type of nanofriction? It was really not experimentally accessible for a long time. Just since 2015, people start dealing with it. And in our case, it would be ions trapped in an ion trap. There was a proposal to study this nanofriction system with the help of a standing laser field. So putting a cavity around the ions and having a standing light field that would mimic basically a substrate, a solid state body, and then you could slide the ions on top of it to study this nanofriction. And there were a lot of theoretical proposals on that. And what people expected from the theory side was that, first of all, you should see some phase transition from sliding to pinning. So when the interaction with the corrugation potential becomes stronger, the atoms will get pinned and there's a symmetry breaking. And what we also would observe and expect would be a soft mode, so some phonon that has a finite frequency, but at the phase transition becomes zero. And this is when they're free sliding. However, if you have a finite system, actually this vanishing of the friction and the vanishing of this phonon will happen only on a single point, exactly at the critical point. Afterwards, it will have a little finite frequency because of the finiteness of the system. So this was the theoretical expectation. And there were actually very beautiful results and measurements on this at the MIT and Vladan Vuletic group, who was the first one to publish this with ytterbium ions in 2015-16. He did actually exactly this, putting a cavity, a standing light field around the ion trap, a surface ion trap. And we did it in parallel. At the beginning, we didn't even know from each other. Our approach was different. We had the idea of using this topological defect. We didn't have a cavity in our vacuum chamber. We had no possibility. And for a clock, I also don't want to have a cavity in the vicinity. So what we thought is, okay, maybe we can engineer our two-dimensional crystal, place in a topological defect, and like this we break here the periodicity of the chains. We have a control parameter here on the periodicity, and the interaction strength we basically vary by bringing the two ion stands closer together or taking them further away. Like this we can vary the corrugation potential. And the corrugation potential in our case is not the standing light field, but it's the Coulomb interaction. So we went out to look for the signatures of this phase transition, and actually it was really successful. We were very happy to see a second order phase transition. We defined ourselves the order parameter of the phase transition, and we saw that below the phase transition, it was 0. It was a symmetric free sliding system. And when we undergo the sliding to pinning transition, the order parameter was taking on a finite value. So this is the red points are what we measured in our system. So it seemed to work well, even without this standing wave and the cavity. We also looked for this sliding mode, so for this frictionless motion. The way we did it was we put two laser beams, we focused them onto the ions, one for the cooling and one a bit offsetted to be able to get a shear force, to have some differential force on the two different, on the upper and the lower string. And then we modulated the intensity of the slide force to excite resonances and to search for the phonon. And this is how you see it, off resonant and resonant. Indeed, you got a signature of a resonance when you sweep your laser. And when we plotted this, this is what theory predicted. And this is actually what we measured. So on one side, left to the phase transition, it worked beautifully. Yeah, it was very pleasing. But then just at the critical point, we saw some big deviation from what we expected to see. When we started then doing many body simulations at finite temperatures, we saw that it must be a temperature effect. There must be some strong nonlinearities kicking in due to the finite temperature. And that was a motivation for us to continue this. And actually, just recently, we submitted a paper now before Christmas, where we studied again the phase transition, but now from linear to zigzag. It's also a second order phase transition with very similar physics of the global system, where you go from one minimum to this double well potential. And we studied exactly the same thing. How do the phonons behave here at the critical point? And you see, it looks really similar to what I showed you before, where you expect the black line is the theory, and this is what we measure. And now here, the orange line would be the theory, and the red points are what we measure, and also what now our new theory helps us to predict. So that was a nice collaboration with Hagai Landa and Giovanni Morici. And for the first time, we also got now some analytical understanding and handle on how to describe this nonlinear coupling of this soft mode with the phonon environment, with the phonon bath. So yeah, that was quite pleasing. Yeah, and last but not least, I should mention that if you do these funny games with the Coulomb crystals, actually this is really physics that's very universal. And we were happy to see, for instance, that this sliding motion, because of a defect, a topological defect in the system, actually even exists in the human DNA. So in our cells, in our DNA strands, if there are sometimes defects in the proteins, and if you have such a defect present, then it actually helps to unfold the DNA and it can break and slide easier. So that's the same friction physics than what we investigated with the ions. And at the moment, we started a new collaboration with Luis Santos and Hendrik Weimer and a PhD student. And the next steps that we're trying to study now in this many body systems with topological defects is basically energy transport, because the defect gives us a handle and a control parameter to either allow energy to tunnel through and to spread out over the system, or to block and locate the energy in one part of the Coulomb crystal. So This is something that we also published 2020. And this is where we are going now in experimentally even further. Okay, I think I'm slowly coming to the outlook of the talk, 45 minutes. As I promised you in the very end, I tell you a little bit about the technology, about the trapping platforms that we're using and developing. So one further step of development that we did in the last years was within a BMBF project, which was called Optical Clock. So the goal of Optical Clock was to put such a messy physics setup of an optical ion clock into a cleaned up rack system. So everything here should go just in 2 racks, the physics package, all the lasers, the ultrastable cavity, everything. So really make it compact and miniaturize. And a part of the project was also to miniaturize and downsize our chip ion traps that allow us then to do many ion multi-ion clocks with ytterbium in the system. So we set up basically a physics package which is compatible to the Optical Clock setup. This was done in a collaboration with Christoph Wunderlich and Professor Meschede in Bonn. So this is how it looked like. We developed a small ion trap which is integrated here in the carrier board directly connected to this. And actually the carrier board is already a part of the vacuum chamber. So you see the ion trap is sitting on this carrier board with the feed throughs to the outside, and the vacuum chamber is really small. It's just this glass cuvette on top of it. I should say this already has successfully trapped ions, and we're doing spectroscopy there now. Other ion traps that we have developed for other people and laboratories in the world, or for instance for Geoid Ikemer's helium setup in Amsterdam, Andreas Schell in Hanover doing nanoparticles, then the ytterbium ion clock at PTB is using now our trap design for the ytterbium-strontium combined clock. And then we're developing also now a portable aluminum clock for the DLR to do the relativistic geodesy that also carries in our ion trap. And another BMBF project that we're investigating right now is Ideal, where we're for the first time going to integrated optics, because I believe the true scalability we can only achieve if we integrate the optics, the light delivery, but also the detection. Only then I can dream of my hundreds of ions. So this is together with German industry partners. And now with the very recently established Quantum Valley Lower Saxony, where Hanover actually wants to build a quantum computer with more than 50 qubits in the next 5 years, our part in this is to also investigate for the first time now integrated waveguides, so that we can really dream of a quantum computer on a chip, or in my case, a clock on a chip. So this is now the direction of technology improvement that we're pushing in the next years. And I would like to make some advertisement along these lines for the very new user facility ion traps that we're right now setting up. So we're working on this now for 2 years, and I believe this year we'll finish everything. And this is actually a service that PTB will offer to industry partners, but also to academia and research partners, where we will provide a dedicated experimental setup where we can do very fast characterization and very fast benchmarking of ion traps. And most important, under a reproducible and standardized setting and environment, because this, I think, is always a big problem, especially when we're comparing heating rates from one lab to the other, and everybody is using different electronics, has a different noise in the lab, and different parameters. It's really not reproducible and standardized. But this dedicated setup will allow us to do a very fast change of ion traps. So there's no PhD student who has now an interest in doing fundamental research and refuses to take out his ion trap. So it's really a dedicated setup where we can characterize one ion trap after the other in a very fast and standardized way. We're also working with the Dean and the CEN-CENELEC on the standardization focus group for quantum technologies, because certainly now that quantum computers, clocks are getting closer and closer to industry, we need the standard values. And with this, I just would like to let you know, so if you're interested and maybe also develop ion traps, that we can help you out there at PTB. At this, I'm at the end of my presentation. Thanks to the team who is doing the excellent work in the lab. And if you're looking for a PhD postdoc, let me know. I'll send me an email. And thanks for the attention.
Thanks a lot for the very nice talk. Like also pretty impressive looking ion traps you have there. For everybody who has a question, do it like Dima Butger and raise your hand, and then we do it maybe yeah, one after the other. So Dima, you start.
Yeah, first of all, Tanja, thank you so much. It's such an interesting and exciting talk, and everything was easy to understand. So thank you for that. I have a quick comment in response to Jamir's question, and then a question to Tanja. So my quick comment, maybe a little provocative. Jamir asked whether there are some improvements due to some quantum things like squeezing or entanglement. And I should say that I just know examples that you can count on the fingers on one hand, where these things have actually helped for something real rather than a demonstration. That's exactly, I'd like to support what Tanja said here. And these examples are actually already mentioned, this idea of Hartmut-Hafner's with two entangled ions for Lorentz invariance measurement. That was really a major breakthrough. And to me, it was actually the first example where entanglement I saw really help. And the second one actually is Ferdinand's magnetic gradiometer, also based on two entangled ions that is insensitive to the magnetic field, but specifically sensitive to gradient. But I really don't know other examples. Maybe somebody can tell me. But despite of the 40 years of effort by many people to use these things for sensing.
I mean, if I may reply on this, Dimitri, there are certainly a couple of highly interesting and beautiful applications of entanglement. I'm also thinking of like Roy's group in Israel, where they're measuring quadrupole moments and do metrological measurements using entangled and squeezed systems. But the way I understood Jamir's question was related to clocks, like in optical clocks and using time and frequency standards for metrology. Indeed, there is no entangled or squeezed system at the moment. So when we are talking about this 10 to minus 18 or so, it's always a classical interrogation. And the problems there are always more on the technical side, and the improvement of a laser system or so always will give us a much bigger level in improvement than the entanglement. Yeah. This is maybe because these systems are just so good and well controlled. That's why entanglement is a hard time. I believe probably as soon as we can scale up really the ions, maybe we can really start playing then with entangled ions in such a well-controlled environment to get a bit improvement in the short-term stability.
Yeah, well, it's true. If you demonstrate at least some real things like these examples that you said, then it means that it really can give an advantage. So
if the question is to have a clear advantage, I see perfectly your point. If the question is good results in beating, for instance, shot noise or reaching the Heisenberg limit, in cavity QED, people do that. Of course, then you can ask, what is this really useful for? Do you get, let's say, precision test of the standard model with that? Not yet. And that was, in some sense, the question I was asking to Tanja and related also to Junior Lab. But this is a problem for us, right? Because if we don't prove to the world in, I don't know, 10, 20 decades that quantum stuff can be really used to outpower challenges of measurement, then they will say, well, then, sorry guys, that's classical physics. I could have done it with a pair of springs in my life 50 years ago. And it's a big trouble for all of us. So I think it's always important to stimulate this type of thing. That was the sense of my question.
No, I mean, you're certainly right. I mean, first of all, we shouldn't give up, because also building a quantum computer takes much longer than we thought in the beginning, right? It's challenging. But we're working on this too. I mean, in Hanover, we, for instance, have this joint research, collaborative research center, the SFB DCOMAT, where we're together with theorists, also Stringarian people involved like this, where we're looking for new strategies, how to enhance and improve actual frequency standards in metrology entanglement and squeezing, because it really depends on the noise. Usually if you entangle ions or atoms, and then you have a bad noise in your laser, this is also enhanced. Yeah? Not only the sensitivity is enhanced, but unfortunately also the sensitivity on the noise source of the laser. And that's why you don't win in a total. And so this is one of the big goals of this SFBT COMAT, that we're trying to investigate modeling new measurement protocols and at what place entanglement or squeezing really helps, and on which other place it has actually disadvantage. So this is ongoing research, and I'm happy to get support there from also outside, of course.
I also had a question actually, to, Tanja. So I just realized that the question may also seem like it's coming from a skeptical side, but still. So you mentioned that okay, 10 to minus 18 in a clock is 1 centimeter, okay, and it's also corresponding to roughly 10 to minus 9 of G. But if right, so if you take a state-of-the-art clock, then you are sensitive at 10 to minus 9 G, and also not in a second, but in a long time, as you mentioned. But if you take a modern superconducting gravimeter, its resolution is 10 to minus 12 G per root hertz.
Yeah.
So why would I use a clock and not a superconducting gravimeter? There must be some reason, right?
You know, I mean, gravimeters and clocks are conceptually different. That's what I wanted to point out with this example of the mountain of the Zugspitze, that, I mean, gravimeters are always sensitive to local mass variations, because it's a force measurement. It's the derivative on the equipotential surface, right? It's the gradient. And that's why you have 1 over r squared. While a clock only sees very big mass changes, so really 1,000 kilometer big water changes. It's 1 over r. And that's why the clock and the gravimeter see different signals, and they will complement each other and help to differentiate. Yeah. So if I want to do a local groundwater measurement, I will always do it with the gravimeter. Prospection, people even do with the gradiometer. They go to the second derivative to be even more locally sensitive to some oil or so. But the clock is really more about the general height. So if the whole mountain would shrink in height, that's observed by the clock and not so good by the gravimeter. And actually, sorry, just another thought, that this to have a reference system, yeah. Like if you're going close to the ocean, or you want to know what's the height of an island of Helgoland, nobody knows, because you cannot map it. You cannot bring your gravimeter with the ship there and always level it out. A clock will tell you immediately. You do 1 point measurement and you see immediately the height difference between this point and that point. With a gravimeter, you always have to measure many, many, many data points. Actually, on an average, you need every 2 kilometers a gravimetric measurement to get the potential surface within the centimeter level accurate. It's always just a gradient that you measure with the gravimeter.
Yeah, I was just actually going to ask, because gravimeters, they operate in networks of dozens of them all around the world. So you cannot extract the information you need from a network this way, or...
As I said, to know the geoid with 1 centimeter precision, the network has to be so dense that you have a gravimeter every 2 kilometers.
I see. Okay, thank you so much. Thank you.
So maybe Alexei is waiting so patiently with his hand raised. Maybe we could let him ask his question.
Yeah, hi. Well, first of all, thanks for the talk. That's really nice. Thank you. I had a question. So you mentioned, like, in one of the graphs that, okay, you drive, for example, the octopole transition in order to get the largest Q factor. Okay. Now, have you thought about, so kind of 2 parts. First of all, have you thought about measuring, like, you know, not the octopole, but like the 16 pole or the 32 pole transition? So going even further. And secondly, trying to use some non-linearities. For example, what if you were to measure not with like 1 ultra-stable laser, but like with a Raman pair of ultra-stable laser and say drive, I don't know, like the 32 pole transition by the 2-photon kind of scheme. Have you thought about that? Like, because that looks like sort of the next improvement in Q. What can you say?
Yeah. Well, I don't want to sound too pessimistic, but believe me, already driving the octopole is quite challenging enough. I mean, if you have this super high forbidden transition with 6 years of lifetime, you need, first of all, a tremendous amount of power of light intensity to get a slow Rabi frequency. I mean, a quadrupole transition I can excite within a few microseconds. But the octopole transition, everything happens on a scale of several milliseconds, yeah, even tens of milliseconds. And that's terrible to slowly flip the pseudospin within tens of milliseconds. Everything has to be super stable. The requirement on the laser is extremely high, the phase stability and external things. That gave us also this really difficult time with the even isotope, which was semi-sensitive because everything dephases in 10 milliseconds otherwise. And then because you need so much power to excite it at all, you get enormous light shifts because most of the light, the power of the laser doesn't really drive the atomic transition, which is super narrow. It's basically a delta function, but the rest of the laser and frequency and how to say the power spectral density and frequency scale that goes to couple other levels. So you have enormous Stark shifts, and actually you have Stark shifts on the level of several kilohertz. And you imagine if I want to make a clock at 10 to minus 18, that means I control everything within a millihertz, but I have Stark shifts on the level of kilohertz. You see this orders of magnitude. And that's the big challenge. It was also for the octopole. So it only got at that point when the laser became so stable at 10 to minus 16, or nowadays we even have a 10 to minus 17 laser at PTB, so that you can do very, very slow pulses. And like this, reduce the power a lot. Stark shift goes with Rabi frequency squared, while the excitation is of course linear with the Rabi frequency. And then you also have to implement some pulsed protocols like hyperemsis spectroscopy to do some games on the Bloch sphere and suppress the Stark shift. So that's really a problem. And if you have more than one ion, how can you scale it up? Because if the next ion would have a different laser intensity of only 1% or 1 per mil difference, you already have such a large Stark shift that the two ions not even see the same resonance. And nothing is really homogeneous. Yeah? If you have a Gaussian laser, the intensity changes a lot. If you try to make a flat top, even there you have intensity spikes on the percent level. So everything becomes super challenging with this highly forbidden transitions. Now your question regarding why not going to nonlinear processes, 2-photon and so. Yes, it's also a possibility, but again, there I think the Stark shifts, the off-resonant excitation is a problem. This is when you calculate the Rabi frequency of a 2-photon process, it's also extremely low. I mean, what people are trying now, I mean, actually, this is a proposal coming from Mainz, so probably you're more familiar with it than me, is to use curvatures of the light field. Like when you're driving the octopole transition, actually the intensity is not the only thing that matters. The octopole is more sensitive to the curvature, the gradient of the light field. So it's actually not so smart to take a classical Gaussian laser. But if you engineer the shape of your laser beam such that you, for instance, make a donut beam, which is dark in the center and then has a strong curvature, then you actually also can excite such a highly forbidden transition like the octopole. But you could, in principle, stay in the dark spot in the center and avoid Stark shifts. So I think this is probably more promising than this 2-photon.
Okay, I see. Okay, thanks. Thank you.
Jamir?
Yes. So also I was quite excited by the talk. We are having a nice chat with Dima about this entanglement where we are clarifying ourselves. So there is no need to comment further on that. Actually, I had a question at the end of the second part of your talk. So when you were talking about these solitons. So can you help me to understand what does it mean that the temperature drives nonlinearities? In my mind, essentially nonlinearities are always there. The spectrum is always there, or the modes are always there. And temperature just will tell me how I occupy the different modes. And when you say the temperature induced nonlinearity, I got a little bit lost.
You mean when I was speaking about the deviations in the frequency spectrum, right?
Yes. There is also a statement in the conclusions, right, where you say that these are strong nonlinearities driven by temperature. Maybe it was the same statement that temperature induced I was a little bit lost on that, right? Because I was thinking, okay, even at zero temperature, right, to get a kink, you need a strong nonlinearity. So I a little bit.
Yeah, okay, one has to look very carefully. So what does nonlinearity mean? I mean, here the soft mode gets really zero. So the frequency becomes very, very small. And this is when the nonlinearities kick in. Otherwise, if you're far away, if you have strong confinement, finite frequencies, of course you do have nonlinearities, but on a completely different order of magnitude, on a different scale. So it's about how well do the modes mix. And what you can see maybe here, I mean, how to say, if you have a Coulomb system, of course you always have nonlinear forces. Yeah, like here, the Coulomb system here, this is a picture of the actual crystal. The ions are at the equilibrium positions and you have nonlinear Coulomb forces. But to first order, you perfectly can approximate it by a harmonic oscillator. You can really neglect the higher order terms. So if I would do the Taylor expansion of the Coulomb potential, the third, fourth order and so on, they hardly contribute. Only if I have very high excitation probabilities. But if I have a laser-cooled system and you calculate the cross-coupling and the nonlinearities, you see, okay, the harmonic approximation is wonderful. It's really sufficient. But of course, it's very different when a mode becomes very shallow, and that means the amplitude becomes very large of the vibration. Then you will start sensing a lot of nonlinearities. And look at this double well potential. What's really brutal is when you add the phase transition, or maybe I show you here. Here it's even better to see. So at the phase transition, first the system is in the center and you have only one minimum of the equilibrium position. And when you undergo the phase transition, you have the two possible minima. But as long as you have some tiniest finite temperature, or ultimately even quantum fluctuations, yeah, they will bring the system from one minimum to the other, because in the beginning, the dimple is really small. Yeah? So even if you're ultra cold in a quantum system, you should sense something, some effect that the system can be here and here at the same time. And then you see the harmonic approximation is nothing good at all, because the system, while it oscillates from one minimum to the other, sees any arbitrary potential shape. And this is exactly the scenario where this higher order terms in the Taylor expansion become really significant. And then you can show, this is what we did now with Giovanna and with Haggai, that you really can trace out a few modes that are important. So basically we were taking the two system modes, which were the lowest frequency mode, and looked how they couple under the presence of an averaged phonon bath. So we were not taking all the phonons that are the rest of the system, the ions, so basically the ion environment of the phonons around. We averaged over them and took a mean value. And then we saw how these two system modes were modified due to the phonon environment because of these nonlinearities. And that gave a really, really nice analytical description of exactly what we observed experimentally.
That's clear. Thanks. Thanks.
So, I mean, I actually had a couple of questions, but I think I'm going to, given the time, it's already 3:30. I will use this momentum to write you an email, Tanja. So are there any other questions in the audience? Any maybe last questions? Doesn't seem to be the case, so I think we can close the seminar here. Tanja, thanks a lot for a very interesting presentation. It was good fun and also very nice discussion.
Yeah,
and
thank you guys. Thank you.
Fantastic. Thank you so much again, Tanja.
No, thanks for many interesting questions. I enjoyed it a lot to have some vivid discussion. Great questions. Thank you.
Bye.
Yeah, then take care and bye-bye.
Bye.